Mhm. Okay.
I can begin?
Yes, you can.
Today I'm going to talk about generalization of Kortweg-de Vries equation, namely cylindrical and spherical analogous. They looks like that. They were invented or found a lot of time ago, and they, you can see that they differ from well-known GDEq equation by the two summands in the left-hand side of equations. They strangely, I must admit, depends on time. Explicitly, but such they are, and it is common view on generalization. I have to comment on what this coordinates mean. The t is time, and x is a distance from the border. Well, I consider initial value boundary equation, and the x coordinate is the distance from the vibrator, because my boundary condition are periodic functions. In all cases, it means just the same, but the physical space is different in the three cases. Maybe some transparency will add the fact that these t and x coordinates are not quite the same as you imagine. It is not physical coordinates as we know it. Even in the first equation, or Burgers equation, or GDEq equation, this x coordinate mean the coordinate which moves with the constant velocity, with which is in acoustics this constant velocity is the speed of sound. I can't call myself an expert in all this, but equations are just such as are shown in this first page. This equation may be rewritten in maybe slightly simpler form. The first alternative presentation is when you write only one constant coefficient gamma instead of two coefficients epsilon and delta. And maybe a more instructive presentation is the presentation which is given in the bottom of this page. The equation becomes, the explicit dependence on time now comes to the part which is connected with dispersion and dissipation. Now to the initial value. We are going to study this border condition, and everything else is zero, which means that at the start of the processes, we have an equilibrium, nothing changed, and at the right, I have to add that in such a form as on the first page, when there is minus at nonlinear term, the propagation of waves is to the right, and therefore we ask complete zero at the right end of our experiments. As T grows, the new terms in these cylindrical and spherical equations tends to zero, and the equation itself tends to simple KdV-Burgers equation. I think it's there is nothing to comment. As T grows, you have no this term tends to zero as well as this, and we come to the first equation. Therefore, I want to recall some properties of this KdV-Burgers equation in the flat case. This KdV-Burgers equation have so-called traveling wave solutions. These solutions travels with constant speed, with the same constant speed to the right, and they have an analytical presentations that you can see on this page. In fact, if the parameter delta is zero, is a special case, of course, because in this formula, which describes the KdV-Burgers itself, this delta is denominator. So for simple Burgers, that is without dissipation, there is a lot of traveling wave solutions. It will be used later. Therefore, I'm talking about them with at some length. The formula 7 is presented on this following graph. It looks like a constant at the left part is 0 at the right part, and the break, almost break, it depends on how coefficients are related, in the middle. There are now I'll show you some results of some experiments, that is numerical experiments with these cylindrical and spherical equations for the initial value boundary equation presented before. I'd rather so far would not comment. There are different initial equations, different initial conditions in different equations. This is for spherical. Before that was for cylindrical, and that is cylindrical GDEq Burgers, while before it was simply Burgers. That is without dissipation, and this is spherical Burgers with different initial values, and this wave is propagating to the left. That is simply obtained by just changing the sign before space coordinate. That is how the process goes. This is for animation for cylindrical Burgers. I would like to mention that the amplitude of this shock stays constant during all this process. Moreover, you can see that the median in this fluctuation is not the straight line, but it is convex line. It's better seen at at the first figure here. You can see that it is not straight line. And this is a common, that is not common, but everywhere you have not a straight line, but a convex line. One more example. After looking at these examples, one can easily see some facts about the usual scenario of this process. Some are physically banal, just as this one. Maybe this one is also quite banal for physics. The term sawtooth profile, that is as tooth of the saw, is well-established terminology. This effect was first discovered in experiments, in acoustic experiments in 60s of the last century, and used in many applications, technical, medical, and others. But it was studied for the flat equation in detail. And the last remark is that after this sawtooth decay, and inevitably the graph becomes a declining convex line, which terminated by a constant amplitude shock. And this shock travels with a constant velocity. It is just the same as in the traveling wave solution for Burgers equation. I mean only shock, because the part that precedes the shock is for cylindrical and spherical equation is another form. Here is a straight line, but here is a convex line declining, so convex line. Mainly, I will talk about this convex line because I get an approximation for it, which is astonishingly correct. Well, let's see further. But the first thing I tried to do, I studied the classical symmetries, and find that there are not many of them because of explicit dependence on time, of course. Yet there are such a set, and some results about them are connected in a table. The Y symmetry, if you want to find an invariant solution for Y symmetry, you have this equation to solve. So far, I have no idea how to solve it, but probably after some change of variables, it will crack, but not now. What I can note that there is no Galilean symmetry. Galilean symmetry permits the existence of Galilean symmetry for flat Burgers equation permits the existence of these shock waves, which were presented in a pink form before. So there is no hope so far, so at least as this equation is not solved, so far is no hope to find solutions which produce one parameter shock waves, family of shock waves for Kortweg-de Vries-Burgers equation for cylindrical and spherical waves. I didn't study conservation law at any length, but the equation itself may be rewritten in a form of conservation law. well, if you just remove the denominator, if you multiply by t, you'll have the form which is of which gives we have a form of conservation law. Then we have I give you a standard technique what to do with a rectangle for which this form gives zero result. I would rather not to comment, but it comes to it's very simple, and it comes to such a relation. I recall that n is numbering the type of equation. When it is zero, this is flat equation. But when it is half or 1 over 2, it is cylindrical, and when it is 1, it's a spherical equation. The right hand side is hard to find because as it is easily seen on this on graphs which I demonstrated, this summons or terms integrants, this one and this one, have numerous breaks, and how to find the numeric value for this integral, even if you know this, if the middle summand, middle integrand is given by the initial value condition, well, almost never you get a good estimation. Two simple cases when you can get this estimation is when effects of dissipation and dispersion are small or negligible compared to the wave itself. Then the right-hand side may be computed. And it gives, well, these are the results. For flat waves, it is this is an answer for flat waves. This is an answer for cylindrical waves, and this is an answer for spherical waves. These estimations are very rough at the examples which were shown you on the graphs. They gives a mistake which is 30% or no more than 30%, but something like that. You can't ignore the dissipation and dispersion effects when calculating this integral. But it is not 100%. mistake. You can somehow get an orientation. What is the value of these integrals? Another case is which corresponds to not a periodical boundary, but constant one. In this case, u to the square, u square is simply m square, and no breaks and no derivatives exist, and this integral comes to a very simple result, this one, which will be used later. This graph shows what you obtain when you use this constant boundary condition. With graphs obtained for equation without dispersion, but it doesn't mean anything. It's just the same for the case when dispersion is present. Two things I want to underline. The first is that cylindrical wave moves faster than the spherical.
Something wrong with sound. Well, at least I have problems with hearing the speaker.
I think it's the internet because it's frozen.
It's frozen, okay.
Well, about this picture, when you see the development of...
No, we see you, but don't see your screen.
I see.
Well, let's continue.
About this picture, about the right picture, you see the development of propagation of a wave which corresponds to constant value boundary condition. And you see that as time goes, the amplitude of the shock stays the same, and it moves with a constant speed. Like it seems as time is a homothetic factor in this first line, and then it goes and goes as sine of x converts to sine nx. Therefore, the solution of such a of such a form, I tried to find in the form of self-similar or homothetic solution. When you substitute it in cylindrical or spherical equation, you obtain this equation, ordinary differential equation, which is hard to solve. But for t large enough, you can omit this last summons, two last terms. Then these solutions, which then the equation which correspond to a, well, how to call it, the Riemann equation for the cylindrical and spherical waves is solved, and you obtain such a solution for these ordinary differential equations. Of course, it includes constants which are to be found. Here you see to be not very misty, I gave you the definition of it. The main thing is this line. Well, how to find this constants? At the shock, we have the x coordinate is v by t, and the amplitude is v. Substituting, we get the final form of approximation to the convex line, and it is shown, the result is shown on the left part of this figure. The solid line is the solution numerically obtained of the Kortweg-de equation in the case of constant border equation, and this is approximation. Well, it visually coincides, of course, but you have this tail which goes over the shock. Here is shown what we want to obtain, not only coincidence with the convex line, but here is shown mainly for which equation and conditions these figures are obtained. Well, here the main step. Since this shock is very much like the shock of Burgers traveling wave solution, we may truncate this dot line simply by multiplying it by this traveling wave solution for the Burgers equation. This is Burgers equation multiplier, which is the same for the spherical and for cylindrical case. Of course, V is not the same. I showed you a figure when there was demonstrated that V for cylindrical wave, this V is more than this V, which is V for spherical equation. And this simple procedure produces just what we wanted. This is U tilde U approximation, which gives you just what is needed. This looks somewhat, well, voluntary, but the effect is very, very good. Some well, I have to explain my terminology. You see, this dots line is prolonged to the very start of this graph, which represent the periodical boundary condition. And you see that the approximation for the monotonic part prolongs as the median part for periodic approximation. It is, well, the periodic oscillation are not around the straight and horizontal line. They are over this convex and monotonically declining line. This allows to estimate the quality of this approximation, not by the site, but also numerically. I found a good animation. And another one. Yeah, they are all the same. These approximations, truncated approximations of approximation to dispersionless and dissipationless equation. This is such an approximation. This is truncated variant. Gives you a trapezoid, this one, which space can be evaluated. It comes, this trapezoid is a median of the solution.
We again have problems with sound.
Presented in, sorry?
Again, problems with sound.
Черт. Щас. Так.
Well, say something.
Не слышно опять?
No, no, it's okay. Now it's okay.
Oh, okay. Well, let's. Then it is the estimation for the integral which comes into the conservation law. But it is obtained by this this approximation. But it may be evaluated numerically. These values are numerically found in a process of solving the differential equations, and it may be put automatically to this integral and obtain the numeric result. The difference between the result which gives you this those approximations and direct computation of this integral are about 1%. Then this difference is
Again, problems.
obtained the shock in Kortweg-de Vries-Burgers equation is not quite the same as the shock in Burgers equation, because the dispersion means that in the corners you have multi-oscillation. They are small, of course, but of course they are not they are not be found in these formulas. Therefore, this small but very small indeed difference between calculation by the ad hoc formulas and direct numerical calculations. Well, so
Well, no sound. No reasonable sound.
the value of V the connected. But
No, Alеш, it's impossible. Nothing is. Alesha. Everything is frozen. Oh. Alеш, can you hear me? Ну, опять, слушай, надо, значит, опять попробую. Ага, вот сейчас ты появился. Давай как-нибудь...
ну, давай, вот если меня слышно, слышишь меня?
Да, сейчас слышно хорошо. Давай такой синапсис.
Слово заключение скажу, и все. Там, ну, это уже, конечно, возможное дело. Да, значит, well, I'd like to well, tell last words about what have been done. You can read it in case I will not be heard again on my window. Simple explicit formulas were obtained to describe monotonic path and its median lines for approximated solutions. We used the technique which is usually used when these equations are created. Ignoring some summands and terms, then ignoring other summands and terms, but the result is very good, at least in all examples which were tried. Some questions still remain. The strange thing is that there exists one parameter family and no symmetry which it must correspond. And I'm sorry for inconvenience which was created by my internet. Thank you for your attention.
Okay, thank you very much. It was a pity that these technical problems aroused. Nevertheless, if participants have problems or remarks, they are welcome. Any questions, any comments? Okay, then we finish for today and meet in a week with the lecture by Petya Pushkari. Have a good week and good night.
Right.